Thank you, Oleg, and hi, everyone. Thank you for joining. Today, we're going to talk about runtime procedural character generation. And don't worry, we'll unpack every word of the title as we move along. Before we begin, I thought I'd just give you a quick introduction of myself. I started my career at HiQ, which is an IT consultant. There I worked mostly with banking, but also in gaming, and this led me to DICE, where I spent most of my career working on Battlefront and Battlefield games. Moving on from DICE, I tried cracking the self-driving car nut for a while at Sensuct before moving on to Goals, where I am now one of the co-founders. There will be more opportunities to hear about Goals during the event, and you're always welcome to stop by our virtual booth in the expo area if you have any questions related to this presentation or Goals, or, of course, opportunities at Goals. So let's get started with the fun stuff. The intention with this presentation is to give you a quick survey of the field of procedural generation of content, and give you some insight into game characters, just so that we can spark interest around this topic. We will end with some kind of extrapolation into the future, what this could be used for, just for fun. So, procedural creation of content. Note that I'm not saying generation now, that comes later. Procedural creation of content is probably easiest to explain by talking about what is not procedural creation. The opposite of procedural creation is sometimes referred to pixel by pixel or manual creation of content. And if we consider this pixelated character in the image, and we want to create so let's imagine the screens only have 12 by 12 pixels for simplicity, and we want to create this character. Then we would paint each pixel black and eventually end up with this character. If we wanted to create another character, we would simply manually do the process again, and the second character we create would also store each pixel color value. Obviously, there are clever ways to store data these days, but that's not the point. The point is that manual creation of content scales really badly in terms of creation time and also storage. So what if we, instead of manually painting each pixel, wrote a small program? Maybe it's something like a line to the top of the center of the body, draw a symmetrical elliptic shape with the parameters x and y, while x and y vary between z and I. Z and I then would, of course, be fixed limits we set on these parameters, and then we can vary x and y to create different heads. The body has to be defined as well as the rest of the character, so that we can find the interesting points to draw on. But the thing here is that now we can vary just these two parameters and create large numbers of characters. If we then move on to generation of content, the word generate implies that we have some kind of automated process to do a lot of stuff, a lot of similar stuff. And now, as I said, we can vary x and y, but we can also pass some kind of list into the algorithm. Let's say it's a list of colors, red, green, and blue. You can imagine large sets of these lists in Excel sheets or other databases, so that we know exactly what comes out of the procedural algorithm. Or we could just input random values for the pixel colors. That would yield a character that we might not have imagined. But that could also be dangerous, because if we get a gray character in this world, we can't see it. So random inputs, completely random inputs, needs limiting for the max and min values, and usually a lot more testing, because it's less deterministic. But this brings us to the next topic, which is random numbers. And random numbers in computers are fun. So they can either be true random numbers or pseudo-random numbers. And the reason this is such a complicated problem is, of course, that computers can't make stuff up. They just do what we tell them. So given an input, a computer will, if it's not broken, hopefully generate the same output every time. But to get around this, there is hardware. In this image, there is a small Arduino add-on. I don't remember which technique this one used, but the point is that you can, so usually for these true random number generators, you can either count the nuclear decay, or you can modulate analog signals and then amplify them a lot to create true random behavior. And true random behavior is very important if you do, for instance, encryption. You don't want someone to be able to figure out your random number based on the input. And it's also a nice feature in a lottery, for instance, if it's actually random. But pseudo-random numbers are different. And they're actually the most common way we use random numbers in computer science. And usually it's enough for your everyday programming and games applications. A pseudo-random number will always generate the same output given an input or a seed. This seed could be the Unix epoch time or whatever, but the point is that it will never change given the same input. So hold on a minute, they're not random at all? Well, no, they're not. They're basically just procedural number generators. But for us, this is a really cool property. This means that given a seed or an input, we could generate the exact same outputs or random numbers, which would be used for a character. And this would mean that we could generate, with just a 64-bit integer as a seed, 18 quintillion different outcomes. That's pretty cool. So you can, from just a 64-bit integer input seed, we can have 18 quintillion different characters if they're 100% procedural. So this is about where my head exploded the first time I grasped this. And let this sink in for a while we talk about the game characters, so we can connect the dots later. Game characters are usually made up of a rig and a skeleton, model or a mesh, and a skin and textures. And nowadays, with advanced cloth engines, we also have, usually clothing on top of this. Previously, clothes were part of the mesh and the skin. But let's start with the rig or the skeleton. So the skeleton in game characters are not used to keep the body upright, as in real life characters. A real life human or animal will just fall in a pile of skin if it doesn't have bones to hold it up. But game characters don't have that property. We can keep them upright without the bones. The reason to have a skeleton is to be able to model the movement of other parts of the body when a given part of the body is moving. So let's say my hand is moving left and right, and what happens to this bone? So that is why we have these rigs or these bone hierarchies. So as you can see in this image, this is a very standard setup where usually you have the rig or the skeleton is built up from the hip going outwards, so it goes up to the spine and then eventually ends up in the hands and the head, and the same for the legs. These skeletons are fully defined by the joints, which are these circles or balls, and the bone length in between them. So the bone length is essentially just the distance between two joints. And as I mentioned before, when you move one of these joints, there are rules on how to move the other adjacent joints, and that is what animation is all about. And you do this in several time points or keyframes, and that's where you have animation. So for our use case, if we want to procedurally change the rig, as long as we keep the number of joints to the same, and as long as we don't vary the bone length too much, we can just send in random numbers for the bone length. So let's vary them a bit. And this, in theory, we could create endless variation of the skeleton and the rig. So that's good. That's really good for procedural generation. Now we move on to what is arguably the most complex part of a character. So this is the model, which is defined by the mesh. And the model is essentially, it's made up by a number of dots in space. They're called vertices. Between these points, so you have I've marked them in the presentation as these gray circles. Between these points, we have lines, and they're called edges, and together they create a surface or a face. And in this particular mesh on the picture, it's made up of quads, meaning 4 vertices. And you need at least 3 vertices to create a surface. And that is why you often hear talk about triangles when people talk about graphics in games. So if we want to manipulate this mesh, we could simply move a vertex. So we could send, so all these vertices have points in space defined by a standard Cartesian coordinate system usually, and you can just send a random number for moving this vertex. This will become very hard though, because you will have very unpredictable behavior, and your model or mesh will look very strange. So instead, you can imagine that you have you build with classical modeling. You build 2 extreme characters, like a very thin one and a very heavy one, and then you could have better rules for varying the points of these vertices. And you can also group vertices, and you can also do this. So you can do this for noses, cheeks, and everything. And now you're probably envisioning some kind of character creator in front of you, which is exactly what I'm talking about. The difference would be that we will vary these inputs randomly. To manipulate these vertices, that's what programs like 3D Studio Max, Blender excel at, by the way. Yes, moving on. So now we have a model, like a clay figure, a gray clay figure. We have to skin this one somehow. And we could make our lives easy and create something like the Blue Man Group and use the same algorithms we did for Pixel Dude before. But we probably want something more sophisticated for our characters. And to the right here, you see a model created by my old colleague, Björn Arvidsson. And if you look at this character, it's kind of daunting to think about how we could possibly generate something looking so realistic. Luckily for us, thanks to other businesses, procedural textures, and specifically for human skin, has gotten really far. So, and we can also add variations for scars with some shader programming, some tattoos with decals, and we can create endless variation in here as well. And depending on the style of your game, you could have the Blue Man Group as well, right? That's totally fine. Now, there are other tools on the market to create characters, and you're thinking, why don't you use them? So this one, for instance, this is a screenshot from Epic's MetaHuman. Really cool stuff. One could think, one can imagine that you vary the. Sorry, MetaHuman is it's a cloud-based service, and you log in, you create your character, and then you can export them and use them in Unreal Engine. As you can see, it's really high definition, high quality, and one can imagine that you vary these inputs, and you can create endless variations of these characters, thereby having a procedural character generation tool. The problem with these models is that so one thing is that it's cloud-based, right? So it's running in the cloud. We don't know how many resources he uses. We don't know what kind of assets they use, and once they're made, they're quite heavy to store. And this brings us to the goals use case, because not only do we need to scale the characters, but this is true for every game. It's just it's just about delivering different level of details, right? Scaling it up and scaling it down. But we cannot have our characters on disk. And the reason is that we need to create millions of unique characters. So millions of unique, high quality characters. And they don't even exist when we ship. And we need to generate them completely without manual work. And by doing so when we did some calculations and we did some prototyping, we figured out that it's not a nice way to do it by having the user download the characters every time you join the game. Eventually, you will probably cache a few of them, but the cache will grow insanely big. So we cannot have them in the cloud. It's impractical and expensive as well. So how could we do this? And now it's time for the first word in the title, which is the runtime part. So all we have done, all we have talked about today needs to be done at runtime. And that means while the game is running, after the game has started, essentially. This is sometimes referred to as online procedural generation versus offline. Offline being you do it beforehand, and online you do it live, essentially. So when you boot the game, you would get a list from the backends with the seeds that belong to you, that you have the right to use. And then we feed them into our procedural box, and we create the skeletons, the meshes, and the textures that make sense for Unreal Engine in the goals use case. And then we instantiate everything. And to change this, we could simply update the procedural algorithms. Or when I say change this, I mean add new features or new materials or whatever. So this is really cool. Now we can have endless numbers of characters in our game. But another thing that hits you when you think about this is that every character is already in the game. All the 18 quintillion characters, the variations, is already in your game. And that's a very different way to look at the games and game assets, as opposed to traditional content. So extrapolating a bit into the future, what if we took these procedural algorithm boxes and created engine adapters? So we had engine adapters for Unreal, for Unity, for Frostbite, for Lumberyard, for all these engines. And it's not inconceivable to have a company that does only this. Now you can, provided that you own a seed, you can pass it into the algorithm and you can move your character around in different engines. That is pretty cool. Obviously, it's up to each engine to implement, but if you have the same company or entity building the engine adapter, they can make sure they look kind of the same. You will have different effects and different possibilities in different engines. But still, it will be your character that you move around. And this, I think, is the holy grail of the metaverse, which is a very hot topic right now. So that's basically it. If this sounds exciting, I would recommend you come work on it at Goals and share your work with the world. Thank you. Questions? You have to help me, Oleg. I guess I'll just start answering questions in the Q&A tab. Is that correct?
Yes, Göran, or I can read those, whatever you prefer, but you can read them.
I can read them as well. So here's a question from Vasya. When you talk about generating different skeletons for the character, is there a way to feed biological, physical realism response into the system so that the character stands, sits, moves, interacts in ways that randomly generate proportions justify? Well, oh yeah. So in terms of the skeleton, as I mentioned, it's nice to keep the number of joints and the skeleton kind of the same, just varying the size, and that's just because we want to be able to reuse a lot of animation. So for our use case, which is the one I can speak to, which is it's a very physical sports game, we will have, so it will depend a lot on the animations looking good. It's different from a game where you have, say you have a wizard standing 20 meters away throwing spells. You can basically do whatever you want. But the point where we want to create the individuality or the kind of the body language for our players is when they're not actually playing. So we call it the idle states or idle poses. And this is where we will add procedural algorithms to the animations as well. So you can envision the angles being varied, and you can envision the max and the mins being varied, and you can also imagine facial features like twitches, or you can have smiles and stuff like that. So maybe that answers your question. And in terms of proportions, a number that is thrown a lot around sometimes is like plus minus 10%. If you want to do it fairly out of the box, you can vary the character size about 10%. Otherwise, it's going to be a lot of manual or procedural work to make the skinning look good if you vary the rig. So I hope that answers your question. I'm going to click mark so I can keep track of them. Okay, what are the most important optimization aspects to look out for when implementing a 3D procedural character generation? So this is not my field, just to push on that. I think so obviously effects are very expensive, but now my brain is on animation because we just talked about it. But so physics-based stuff is expensive. In our game, has to run on really low-end rigs. We're gonna shy away from a lot of stuff like that. We might have ray tracing for arenas and stuff, but we never want to have advanced graphic stuff affecting our players or the game, because it has to be 100% fair on all platforms, because we are cross-generation as well as cross-platform. So looking at the optimization aspects, remove fancy stuff if you don't need it, but otherwise you have to talk to someone that is good at the 3D stuff.
Maybe one more question.
Yes. Jesse asks, are you familiar with the wave function collapse, and have you had any use cases for it? Short answer, no. Sounds familiar. Sorry. So that was a boring question. Oleg, can I do another one?
I'm going to ask Veniamin, Arin, and Boris. Can you? I copied the questions, but can you actually paste these questions on the goals website, and maybe Göran, you can answer it a little bit later.
Well, yes, it's really interesting questions, by the way, people. So I'm going to read them for sure, and I will make sure they get back to you somehow.
Yeah. I also copied the questions, so thank you very much.
Okay, thanks, Oleg.
Thank you, everyone. Thank you.
Thank you, everyone, for listening. Bye.